Hello, everyone, and good morning. So, let us start our discussion on some very useful concept in machine learning model development. Specifically, we'll talk about the concept of overfitting and underfitting, bias and variance, and regularization and their techniques. Specifically, two kind of regularization, that is L2 and L1 regularization, L2 or ridge, and L1 or lasso regularization. So these are all very, very useful concept in designing a machine learning model. Also, working with a machine learning model and to understand how it is responding to the data. So these concepts are essentially very important. So let us start. Okay, you see, uh, suppose I have some data like this. Okay, this one, this one, this one, and again we are trying to make a model for housing price data. So this is a feature, important feature called floor area, and this is price. And one of your friends, he decided that he or she decided that my predictor will be very complicated, okay, and so as to make my predictor pass on the each training data, so that the cost function value will be 0. And to achieve that, she has incorporated so many parameters with the higher order term of the features, W1, W2, W3, W4, W5, etc., etc. Now, while this kind of model will be able to predict pretty well within the domain of training samples, but the moment it is actually you are trying to use it for other domain like here and here, and specifically we develop machine learning model to predict beyond training data, right? That is its main advantage. But in that case, this will miserably fail. Okay, so this kind of design is called overfitted model design, and in another term, technical term, it is called that this design has a very high variance. So this variance actually term is not in the sense of statistics, but variance essentially mean that this model has several parameters, maybe more than what is necessary. Okay, so this is bad, right? Because, and we call it overfitted model. It is bad, again I am telling, because it will fail to predict the price of the house beyond the design data like this. Okay, so, and we essentially design model so that I can predict in this zone, I can predict in this zone where actually data is not available. So in that sense, it miserably failed. Okay. Now let us see another scenario. Say your another friend on the same housing price data, while the data trained is like this, she decided no, this will be my predictor. Okay, I will assign very few parameters and make our design very simple. The predictor design is very simple. Okay, irrespective of whatever is the trend of the data. This kind of, and this is again bad. Why bad? Because it will not only fail to predict within this training zone, you see here, even here, the prediction error will be high. It may fail beyond that also. So this type of model is called underfitted model, and in technical term it is called high. The model has high bias, means I am so biased about my design, I don't care about the samples. Okay, so it is high bias and essentially low variance. Low variance means you see too few parameters, and which will fail to capture the pattern of the data. Okay, so again this is bad. And here again you see that I have data trained like this, and if I design a predictor having having optimally required parameters, you see I have not unnecessarily put parameters like W3, W4, W5, Wn, like. So it seems to be that, okay, 1, 2, 3 parameters having some parameters attached with the higher order feature will be sufficient to capture the pattern of the data, and it generalizes well, means it is in this zone also it will predict well, and in this zone also where I do not have data it will predict well. So this is called best fitted model, and it is also called that the model has proper bias and proper variance. So the concept is very simple. So I need to, based on my data, I need to fit a model which will optimally best fit the training data. If it fits best in the training data, it will generalize well beyond training data. So that's our hypothesis, which is grounded on a very logical understanding, okay, logical concept. So you see, high bias, high variance and low bias, which creates, so now we are summarizing, high variance and low bias creates overfitting. This is okay. Low variance and high bias creates underfitting problem, and optimal bias and optimal variance, which is required, create best fitted model. Now the question is how to know, given a data, how to know that, well, these are the optimal parameter which my predictor should have. So the idea is, can you automate? Let the training data tell how many parameters should be there. Can you automate the design process? Answer is, to some extent, yes. Using regularization process, we can automate the predictor design process. Now we are going to discuss more about this, how it is done, how regularization can help you in automating the design process. And we will talk about two regularizer, ridge regularization and lasso regularization. They help in understanding that, okay, if this is the data set, these are the minimum required parameter. And how we are going to do that? The idea is, again, let us be democratic. Democratically, you can select, assuming that there are complexity in the pattern, you can select many parameters attached with the higher order feature term. Okay. By the way, in machine learning concept, say x is the housing price in housing price data. If x is the floor area, then x square is another feature. X cube is another feature. X to the power 4 is another feature. It's not a floor area anymore. So floor area is a feature. This is another feature. This is another feature. So synthetically, you can create features in this way, and you can call it. So if it is another feature, you can call it x1, x2, x3, like that. And your frame can very easily design also this kind of predictor. Okay. So democratically, you, as you think that as many parameters you can attach. Then we actually regularize by introducing a term lambda, okay, which is a hyperparameter with high values such as keeping such as 1000, 2000, 3000, maybe like that, and letting wj values attached with the higher order terms be very small, 0.01, 0.002, 0.003. So if your model contains W values like this, it is your choice. You can just remove them, because the features which whose parameters, attached parameters value are like this, maybe those features are not relevant features. Okay. So this is the basic concept, and we are going to achieve this by the process of a regularizer that is specifically, say, I am giving an example of ridge regularization, and specifically we are taking the example. So this is our cost function, okay, mean square error function, mean square error, this is the error, okay, you know, this is the predicted, and this is the ground truth, okay, predicted housing price, ground truth housing price. So this is the error. What we have done with this function itself, we have added a regularizer term. Okay. So what is this lambda j? However, j means the feature, right? J equal to 1 to n, 1, 2, 3. But normally lambda 1, lambda 2, lambda 3, these actually are kept constant, one value lambda. Otherwise, there will be too many hyperparameters which you need to determine. Okay. So this is what lambda is a hyperparameter. And now we have kept, you see, summation of wj square. J equals to 1 to n. N is the number of features. So this is the number of samples, m is the number of samples, and we are assuming the sample size, if it is m is sample size, then n is the number of features which my data has, and my predictor should have parameters attached with each of the features. So this is my parameter, wj square. Okay, so this is regularizer term. Now try to just see, this is my basic gradient descent model, right? That is new assigned wj, w equal to earlier wj minus alpha. Alpha is the learning rate, as you know. Learning rate, as you can see, na? So this is basically a step length. Okay, so alpha value equal to 0.01. Step length is very small. Alpha equal to 0.1. Step length is big. So optimal alpha value is required. So the alpha is actually learning rate or the step length of the iteration. Okay, so this is my main algorithm. Now I need to determine the derivative of this function. Okay, and as you know, now the repeat till convergence. So this is how algorithms start working. So this is bias term. Bias term is not normally regularized. So we have not attached this term here. Why? The reason is very simple, because through regularization, we are trying to understand what are the features which are relevant. Those features will be relevant with which the attached parameter value are significant, and those features are irrelevant for which the attached parameter are just like w values, wj is just like 0.01 or 0.002, like that. So those are irrelevant features. Now if there is no feature attached with the bias, then there is no question of actually regularizing the feature. As you know, the feature attached with W0 is X0, which is a fictitious feature, right? And this is always equal to 1. We keep normally 1. So that you know. So that's why we are not regularizing the first term. And then we are regularizing the all other term, okay? Wj, new assigned value equal to earlier wj minus alpha by m. So this is the derivation we have done. That is the derivative of this function, right? And then derivative of this function. So this minus plus minus. So alpha is there. Alpha is also there. So that's how alpha times this. So this is a function. Alpha times this one. So alpha lambda divided by m. So m as it is will be there, and 2 and this 2 derivative cancels out. So the second term, alpha lambda divided by m wj, is the derivative of the regularization term. Okay, this is the derivative of the cost function. Okay, without regularization. So you understand that, right? And you see, so you have wj here. So I can do a little arithmetic. Okay, so 1 minus alpha lambda divided by m times wj minus this term as it is. Okay, Now say I am running my gradient descent algorithm. There are so many features which I have taken, W1, W2, W3, and in vector form they are being upgraded. So when all the vectors will be evaluated for a particular step length, then second epoch will start. Okay, this is called epoch. So there is a difference between epoch and iteration. Okay, so this is the iteration, iteration for tuning a particular parameter, and when set of tuning is done, then we go and repeat the same process, which is called one epoch. So if there are 10 um, um, parameters, for example, so after all parameters, 10 parameters are evaluated, next step of the um, epoch will start, and this will continue till the parameter values reach to our um, allowable limit within which, I mean, if the parameters are not changing that much, okay, maybe you give a threshold minus 10 to the power minus 2, and if W parameters are not changing or the JW is also not changing much, that means what? That means JW has reached, okay, so JW has reached here, so minimum value, okay. So if there is no change, appreciable change, then we stop the algorithm and we take W values as fixed W values, which can be used for our predictor design. So this is as simple as this. So look this term here. So 1 minus alpha times lambda divided by m. So alpha itself is small, 0.1, or it is a fraction, 0.01, 0.001, like that. And lambda, you can just assign some 1,000, 2,000, something like that. M is very, very large, 30,000, 40,000, 50,000, like that. So this term itself is very, very small. Okay, it's a fraction, 1 minus some fraction. Now if you see here, if M is very large, that means so what you see here, first of all, the parameter Wj is shrinking itself. Okay, so this is very important. It will shrink. Now the rate of shrinking will depend on m. Okay, these are fixed value for a fixed hyperparameter value. If the sample size are large, so very small shrinking will be there repeatedly, and Wj may stabilize and shrinking may not be that much. Means if m is large, then maybe you need more number of, and you will get more number of parameters. So more number of features will be relevant. Whereas if m is too small, you don't need m is small, okay, small compared to n, so there will be a underfitting problem. Okay, so if n is actually, then n has to be very small, number of features has to be very small, and that will be ensured. You see here, m is small now, so 1 minus something which is large compared to earlier one will actually try to annihilate Wj very quickly. So many Wj will disappear, okay, because now the shrinking rate is very, very high. So that's the regularization. This term is actually determining based on if the sample size is large, okay, then keep make your compared to n, then make a little bit predictor a complicated one, sophisticated one. If m is small, make your predictor simple compared to n, right? You don't require so many parameters on a small data set. You got my point? And if it is, then let us try to understand that how it can be, with the example, how it can be done, how it can be understood. Say, I have housing price data, floor area and housing price, and these are the data, and I am selecting to understand and to make it make you understandable to you by hand calculation. I have selected 2 points, which is causing overfitting, right? Because they belongs to the regression line itself. So objective function, I have just made a L2 regularizer or ridge regularizer by adding lambda and wj square. Here j equals to 1 to 2. Say we have only m equals to I equal to 1 to 2, and say we have two features, two parameters only. Okay. So what? Let the two parameters be on the regularizing line. Okay. So make w lambda 1 equals to 1, w equals to 1.4. So one parameter. Sorry, one parameter we have. So then jw equals to, that is the value of the cost function, 1.96. You can calculate, because this is 0 plus 1 into 1.4 square. Now let us assume that some loss is there for these two points. Like if the points are now a little bit offset from the line, so there will be error. And let, these are fictitious value. Let for, we have 2 points only. For 1 point, let us assume that the error is 0.3. For another point, let us assume the error is 0.2. So the loss will be 0.3 square plus 0.2 square equal to 0.13. And lambda equals to 1, w equals to 0.7. So we are decrementing w, just like parameter is getting shrinked. Okay, if this is shrinked w now, then jw will be 0.62. You see, now the points, as soon as the points are not on the line, that is more generalized line now, and the cost function value is decreasing. So this is what is expected, right? And you see, the earlier 2 points which were overfitted now regularized, now best fitted, okay, through regularization. So this is a very simple example. This is for ridge regularization. For lasso regularization also we can do. We can add a parameter lambda times. So instead of square, lasso actually add this parameter, and then take the again 2 points overfitted, then evaluate cost function, which is 1.4 cost, and then 2 points again take, so that these are the 2 points. Now there are some errors, value is this, and then let lambda equal to 1 and w equal to 0.7 as earlier. So wj equals to 0.13 into 1.0.7. So here also the cost function value decreased, it regularized, but it did not decrease like the earlier one. But it will depend on data sets that which regularizer you should use. But normally this is the most common, widely used regularization process, ridge regularization, L2 regularization, because you can see from here, from the, once you have reformulated the J, then automatically the algorithm, when it is running, this term is allowing the parameter to get shrinked, okay? And how many parameters will be there, that will depend on type of the pattern of the samples, not only the number of samples. Say I have samples like 1, 2, 3, 4, okay, 30 samples, okay, like that, X, W, X, and Y, okay. Same 30 samples if could be like this, okay. Then the this regularizer has the ability to tell you that here the number of parameters will be less than here, the number of parameters will be more. Okay, here you will see the large number of, comparatively large number of parameters will remain, will not shrink. Okay, not all parameters. Here only barring few parameters, all will be shrinked towards insignificant value. So I believe now you have understood the role of regularization, and now we will move forward and we will give you a specific concrete example of um, designing process of a machine learning model with special reference to linear regression model. Till then, stay safe and have a nice day. Bye bye.